Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Jeff Peterson and Veronica Dexheimer with us today. Hi, Jeff. Hi, Veronica.
Hi.
Hey. Thank you both for agreeing to talk about your very lovely article today.
Thank you.
And Jeff and Veronica, where are you located at?
What you want to start there?
You said me to start?
Yeah.
Where are you?
I was in Kent for a while.
Oh, okay.
I'm still enrolled in Kent, but I'm finishing up long distance in a small town in Pennsylvania.
Very cool. Very nice. So is there snow on the ground there in Pennsylvania?
Yeah, it's here. It's melting, but it's here.
Okay. I've heard there was a storm. There's a big northern polar push coming. So you may get a little something extra here over the next day or so.
Nothing new there.
And Veronica, you are in Kent?
Yes, I am in Kent, Ohio.
Mm-hmm.
I'm originally Brazilian, so for me, it's always cold here.
We should get you to move to Phoenix. So I'm in Phoenix, Arizona on this February 16th, 2022 when we shoot this. And we are a little cooler today, but otherwise normally I guess we have a little bit more like Brazil-like temperatures. So did you grow up Brazil near the equator, or were you farther down, or where were you?
I'm from the south of Brazil, so we do have a winter there, just not comparable to Ohio winter.
Yeah. Mm-hmm. Very cool. Very nice. When did you come to the US?
After I finished my PhD, I moved here about 9 years ago.
Very cool. Very nice.
Been in Kent State ever since.
Very nice. Very cool. Okay, Jeff, what do you like to do for research?
I mostly focus on equations of state with temperature and magnetic field effects included.
I like equations of state. Very nice. And Veronica, what do you like to do for research?
I work with compact stars, with more precisely neutron stars and white dwarfs. So pretty much dense matter. In the past years, I also started getting involved not only into high temperature physics, but also magnetic fields. And that's pretty much what led to this work, trying to put everything together and see what happens, because very often only one of these aspects is investigated. Either people work with dense matter or hot or magnetized. We decided to see what happens when you put everything together under strong gravity.
Good. Awesome. And that is going to bring us to this very lovely APJ article. Effects of magnetic fields in hot white dwarfs. And Jeff and Veronica, take us away.
So, as I said, the idea of this paper is investigating all these different features together. This is a white dwarf paper and is an important part of Jeffrey's PhD research. So the idea was to work with some collaborators, which are shown here. Rodrigo Negreiros, which works in Universidade Fluminense in Brazil, doing the general relativity aspect of compact stars, and also Bárbara Castanheira Endel, which is in Baylor University in Texas, which is an astronomer specialized in white dwarfs. So we put this team together. I'm an equation of state, and Jeffrey, as a consequence, is also an equation of state physicist. So what we do when we study compact stars is separately calculate the equation of state and work on the microphysics part of the problem. Usually take into account special relativity. And then when you want to know what the resulting structure is, we put this in a general relativity code to calculate the macroscopic structure, like masses and radii and things like that. So that explains the theme.
Cool.
And so, as I said before, we were combining the effects of temperature and magnetic fields for the first time. in white dwarfs. And what we wanted to do is having a very comprehensive kind of work. So we didn't want to use approximations that are usually used in the literature.
Right.
So we wanted to be able to apply this work for any temperature, density, or magnetic field we wanted. So this made it much harder to solve this problem numerically, because usually what physicists do is look for an approximation that works in a particular case, but we didn't want to be particular.
Right.
And that also relates to some of the things we're going to discuss in the end, I guess, in the outlook. So that's why we wanted to be comprehensive.
Cool.
So I think Jeffrey maybe can jump in and discuss more like the steps of the work that led to our interesting results.
Okay.
So I take it you mean the formalism and such?
If you like, we can talk about the formalism. If you want to cover that, that's perfectly good. Or we can jump down to a figure, your call.
I mean, I guess we can look at the equations first. So
Sure.
I guess we start with number one. Or, well, I guess we can start with this acknowledgement at the top here with the splitting of the integration limits.
Uh-huh.
So with the low temperatures, the distribution function, the Fermi distribution function, is not going to be very far from a step function. So we're seeing a pretty steep drop, and it's not, you know, the smoother drop that you would get at higher temperatures. So in order to work with that, with the integration routines that we had available at the ready, we split the integral, or split the integral into intervals.
Good. Okay.
Listed here.
Okay. Okay. So we got sort of a low, medium, and high.
Right, and that's basically, we're centering that on the chemical potential and just kind of, well, centering it on where it drops.
And just to be clear, that's
and just making symmetric intervals on either side so that that center part where it changes is easier to do.
Yes, yes, it is. Very cool. And so we got a number density of electrons.
So yeah. So, and then I don't know how much into detail I really want to go with this, but yeah. So
let me ask you a question. So this is the, let's say this is the number density of electrons, and B here is a magnetic field. So this is the contribution of E fields, right? Because even if B was 0, the number density of electrons is not 0 in a white dwarf. Yeah.
Right.
So
this is the magnetic component is what I'm getting at.
No, it's not that trivial to do the low B limit of this equation for the fermions.
Okay. Okay.
But it's everything's in there. And you can note also that equation 1 has 2 terms, one for the distribution function of particles and the other one for the distribution function of antiparticles, because after a certain temperature, the antiparticles become relevant for the problem too. So in this kind of finite temperature context, what people call the density or number density is actually the net number density, which is the number of particles minus the number of antiparticles per volume.
Yes. Yes. Here would be positrons, for example. Yes. We have a number density. We have pressure, and we got a specific entropy, it looks like. Okay.
Okay, so trying to parse that.
Good.
Were we done? Were we done with that one?
If you like, yeah. So then we have the grand canonical.
Okay, well, yeah. So looking here, the magnetic field is creating Landau levels from the electrons, you know, going around the magnetic field itself. And that's giving us an anisotropy in the pressure. We have a parallel pressure and a perpendicular pressure. I think you're
Right.
yeah.
Right. Okay.
Good.
Good.
Yeah. So I don't have this all pre-planned, so
All good. It's all good.
I think the pressure appears there on the top of the page.
yeah, he has it. It's not, he's not showing the top.
Yeah, it's the very top.
We
There.
just have a little bandwidth lag between us. It's okay. So you got the parallel and the perpendicular components. Yes.
Okay, there it is.
Wow. Okay. Yeah, we just have a little bandwidth lag. We're good.
Okay. So again, we can see the same factor for the magnetic field out in front. And with everything but the number density, we're adding the particles and antiparticles instead of subtracting. So that we're getting the total pressure and not the net, unlike the net number density.
Good.
And with the perpendicular pressure, we have the additional factor here with the M bar and everything else in parentheses. That is a contribution from the magnetic field as well.
Got it. This is where the reduction comes in. Got it. Okay. Very cool.
And then we have the entropy density, which again has the B factor out in front. So when we're doing, if we do 0B, we're using basically different expressions. And then we have these, 1 minus F ln 1 over 1 minus F. Yeah.
Yep.
Yeah, we have a whole mess of these for all the different distribution functions. Nicely, they have, these all go to 0 at, the distribution function being 0 or 1.
Fair enough. Yes. Okay, so we got a grand canonical, and then of course you got this function here.
If there's anything else I want to say. Yeah, and of course we have the magnetization listed, and that's parallel pressure minus perpendicular pressure over the magnetic field. And yeah, we've stated the distribution function.
Yep.
And then the baryon energy density. So we're working with symmetric matter for the nucleons. So, and we have, charge neutrality. So there's as many protons as there are electrons. And because it's symmetric, there's as many neutrons as there are electrons. And so there's twice as many nucleons as electrons. So our number density for the baryons is twice that of the electrons. And then the energy density, they're not moving as much. So they're not really going to contribute a whole lot thermally. And so we're just simplifying that down to multiplying by the mass to get the energy density.
Yep. Very good. Want to talk about figure 1? Figure 2?
Probably.
Let's do that.
Yeah.
Now that we've got our pressures together, there we go.
All right, so here we're looking at the 0 temperature limit for various magnetic fields.
Okay.
And the one thing that we can really see here is the steep incline and then this first bump, if you just want to point out one of those. Yeah.
This first bump here is you
out. So everything, prior to this is basically we're in the 0th Landau level.
Yes.
And then when this oscillation, this Van Alphen oscillation occurs, we're going from Landau level 1 or 0 to Landau level 1.
Mhm.
And so,
Makes sense.
as we can see at various magnetic fields, these oscillations are generally moving up and to the right for when they start to happen.
Yes. The greater the B is, the higher density it takes to hit that Landau level. Yep.
Yeah.
Very good. And this is the.
And then as we go further, they're converging toward the same line.
Fair enough. Yes.
Toward the B equals 0, which this is a log-log plot, so it may not be much of a line.
Okay. Yes, I get it. I'm with you. Good.
And figure 2.
Ten to the 8th K.
We're seeing the same magnetic fields, but at a much higher temperature of 10 to the 8 Kelvin.
Thermal motion. Yeah.
Which I believe for a white dwarf is going to coincide more with early stages, because triple alpha activization is around 10 to the 8. So this would be younger white dwarfs at this temperature in the core.
Yep. Newly born white dwarfs. Yep.
And this plot also shows nicely how magnetic field and temperature are competing effects.
Right. Let's take a look at both these.
So,
I was getting there.
oh, I'm sorry.
It's all good. It's all good.
Everything is complicated.
Yeah, I just wanted to say, hey, where in the realm of possibility is 10 to the 8. And
Okay.
that's
It's all
young white dwarfs that are newly formed.
Yep.
And of course, we can see for all but the most extreme magnetic fields, these Van Alphen oscillations that we have at 0 temperature are gone.
Yes.
And that's basically the temperature effects have, in the way I would word it is they've won out over the magnetic field.
Yep. That makes sense.
So, yeah,
Cool.
that I think is probably the biggest takeaway. Any smaller details, Veronica? Okay.
Onwards, so we got the it's up to you whether you want to cover figure 3. Parallel function is a function. Oh, there we go. Let's talk about some of these oscillations.
Here we're looking. Oh, we're looking where now?
I just kind of on, let's say, I mean, it's up to you. I'm just going on figure 5. We have the magnetization as a function of baryon density.
Sorry, I think it's important to discuss a little bit of what's going on in figure 4.
Okay.
Right.
It's important to add the fact that we also include the anomalous magnetic moment in this work, because the electrons are fermions, so they have integer spin, and they tend to, when have a strong magnetic field, either align with it or anti-align with it. Depends on their spin projections. And this is something that also was novel that we're investigating in white dwarfs, is adding this interaction between the spin and magnetic field. What were the results if they could be seen? So Jeffrey, I think this is one of the plots in which this appears more clearly, right?
Yeah, so this is kind of showing an intermediate.
Oh, sorry, it's not figure 4. Which is the one in which this appears clearly, that you have the jump? Could you zoom out a little bit?
Sure. Give me one second.
Maybe it was figure 3.
Yeah, I think it was.
Figure 3 was one magnetic field and a bunch of temperatures, I believe.
Yeah. So this is a parallel function as a function of the baryon density for different temperature.
Maybe it was figure 3. No.
No.
Maybe I'm going on linear.
Figure 3
Could you go
because
down?
doing a lot of the temperature winning.
Could you go down a little bit?
Sure. So you
Oh,
got,
there it is. It's figure 6.
okay, let's zoom in on that one. Okay.
Could you explain this one, Jeff?
So this is showing in black and green the parallel pressure with and without the anomalous magnetic moment.
Oh, I see. Okay.
And the red and blue are the perpendicular pressure with and without anomalous magnetic moment. I believe, yeah, solid lines include the anomalous magnetic moment,
Yeah.
and dashed lines do not. So yeah, we're seeing with the parallel pressure, you're kind of the same either way.
Yeah.
But the perpendicular pressure, when we include the anomalous magnetic moment,
Changed quite a bit.
it's not darting down to 0 or darting from 0 at this point where it's changing.
Uh-huh. Uh-huh. Good. Good.
It's,
So you
you
get
know,
a sense of the magnetic the importance of the or non-importance as it may be of the magnetic moment. Yep.
Yeah. And then I don't think figure 3 was the most important of things. It's mostly just showing temperature as it wins slowly, I think. Figure 4 was more of an intermediate step
Okay.
with temperature and magnetic field, and it's more surface temperature range.
Yes.
Of 10 to the 4 Kelvin. With a high magnetic field though, right? We're not going to see magnetic fields in a white dwarf on the surface of 10 to the 12 Gauss.
Okay.
That's a very interesting discussion about this magnetic field that white dwarfs can reach, because what people have been measuring is 10 to the 8, 10 to the 9 Gauss, but we have to keep in mind that this is always surface magnetic fields, and the ones that were more interesting is how this grows towards the center of the star. So in this initial part of the paper that Jeff is discussing right now, we kept the temperature and magnetic field constant because we're just looking at general effects, but more towards the end of the paper, we get more realistic profiles, and then so it's a more realistic case. Then we're going to see how things look when you have a magnetic field that increases towards the center. But the thing is, besides model dependency, there's no way to estimate what's there's no way to measure what the magnetic field is in the center of any compact star. So all we can do is estimate.
Okay.
Yeah, and I kind of wanted to point it out that I really like what this green line, the 10 to the 6 Kelvin one, is doing. Yeah, because we're seeing both things happening at the same time. We're seeing temperature effects showing on the left,
Yeah.
where it's being elevated, but then on the right, we're seeing the Van Alphen oscillations from the Landau levels.
Cool.
So we have magnetic field effects.
Yep.
So I just thought that was probably one of the most interesting lines in the plot.
Yeah, it covers that intermediate regime.
Right.
Cool. Yep. Same thing here.
And then just continuing back to going in order, the magnetization in figure 5 is very packed toward the right.
Indeed it
So,
is. Bang, 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 bang.
Yeah. Yeah. So this plot, I mean, it was difficult to get figured out how to make it correctly because so our code steps chemical potential.
Okay.
And
yeah,
the density starts changing faster as you get higher in chemical potential. So to make this plot even, I had to play around with the code until I was basically going to a point where it
so
I would have it go until it stopped looking good. And then I'd have to go back like, okay, let's take it down a power of 10 in the chemical potential step size.
Oh, yes, certainly.
and then run it from there until it goes again, until it stops looking good again. And yeah, I don't even remember how small it had to get.
That's fine. But yeah, I'll certainly believe the step size on the chemical potential has to adjust as you change density, certainly. Yes.
Well, to get anything that, looks like we can actually use it for a plot in the magnetization, yes.
Very nice plot.
But yeah, the magnetization, we can see oscillates wildly at lower temperatures. And it is going negative, which is not necessarily a good thing. What would that mean? Zero temperature isn't really.
But there are the contributions too. But I think what's interesting from this plot is that the magnetization, it depends on the magnetic field. So for this chosen magnetic field of 10 to the 12, you can see that it has very large magnitude.
Yeah.
Right. And again, we see that as the temperature increases, the oscillations are smoothing out. So by the time we get to 10 to the 8 Kelvin,
thermal ends.
Temperature is mostly just winning.
Very good. Cool. Very good.
So we did figure 5. We already said figure 6. Figure 7, entropy per baryon. Oh, so yeah. Going from, so another way to model the stars, or to basically get a temperature profile. So when we're modeling stars, another way to do it, right? Or a way to do it is we would want to fix the entropy per baryon.
Okay. What's up here? This is S over, right? This is an entropy.
Well, I was thinking figure 7, that's figure 8.
Same thing.
So
where am
I? They're not quite the same. So
here we go.
Figure 7 is fixed temperature showing entropy per baryon.
That's per baryon. There we go. Okay. All right.
And so our fixed temperatures don't have entropy per baryon fixed, of course. But this is just a plot showing it leading into figure 8, which is how the temperature changes, I believe, as the entropy per baryon, or with fixed entropy per baryon.
Right.
Yeah.
Good.
And so then this is ranging over even more powers of density. So I think that's going
10 to the 12.
What would be, almost 10 to the 12. And I think the other ones were stopping around 10 to the 6.
And that goes back to one of the reasons why these compact stars are so interesting, because they cover all possible regimes of density that you can imagine, going from something much more like solid here on Earth to very different kinds of matter that we cannot reproduce in laboratories. So I think this can be clearly seen from this x-axis there.
Cool. Very good. Big dependence on the entropy, of course. Yes.
Yeah, and that is figure 7 and 8, I believe, were both with zero magnetic field. And then
yes.
And then looking at 9 and 10, these are, so wait for them to show up on my screen. Okay. So 9 is, again, constant temperature, looking at how the entropy per baryon changes. And we start to see, or we're seeing again, wild oscillations due to Landau levels.
Bang, bang, bang.
And in figure 10, we flip those around, fix the entropy per baryon, and see how it goes again. The lower entropy one is resulting in lower temperatures. and stronger magnetic field effects. Whereas the higher entropy one is we're not seeing as much from the magnetic field. But we do see a few interesting bits.
Yeah,
They're
right.
around 10 to the, it's really small, 10 to the 4. So right around the surface temperature.
Okay,
then-
yes, right here, 10 to the 4, let's say.
Yeah.
Okay.
And then from here, I believe it starts going into GR, which I don't know as well.
Good. You know, you've got your metric there. Yeah, and then you've got stress energy equation, fine. So how to do thermal.
Yeah, a lot of the GR here was Rodrigo, I believe.
That would be.
And the complication here is that usually when you're calculating a macroscopic structure for a normal star that has low magnetic field or rotates slowly, you can find a very simple solution for Einstein's equations, or the Thom-Oppenheimer focal equations, which are perfectly spherical. They're quite simple. You can write them in one line.
Right.
And solve them very easily too, numerically. But when you have the magnetic fields that we're discussing, what they start to do is to deform the star. We are assuming that the magnetic field configuration is poloidal here, so the star is going to be squished.
Okay.
And the metric gets more complicated, the solutions get more complicated. And not only that, but now you have to solve Maxwell's equations on the top of the Einstein's equation. So they have to all be solved, this large couple system of equations, which are hardly nonlinear.
Yeah.
So finding solutions even numerically is not easy. So we use the general relativity code that was developed by our collaborator, Rodrigo. That used the equations of state that Jeffrey produced in order to find out what the structure of the star looks like.
Cool. Let's take a look at that structure.
Oh, okay. It's my turn. Fine. So the results are shown here first in figure 11. So again, we're choosing temperature 0, a low temperature profile where we fix the entropy to a colder white dwarf, older white dwarf, but taking the temperature into account, this blue line. And then we choose something that, oh, sorry, red line. The blue line is a younger, we trying to represent a realistic temperature profile for younger white dwarf.
Yeah.
And you can see that the temperature in the older white dwarf case, it's not, it doesn't change anything, but for the other one, you can already see how this affects the star. So what we're plotting here in figure 11 and 12 is the magnetic field profile that comes out of solving the Einstein's and Maxwell's equations together.
Right.
You can see that the larger temperature profile, even the magnetic field is coming out differently because of that. So now the magnetic field is not fixed, it's determined consistently by the code. Because if you have a constant magnetic field, for example, you're not going to conserve magnetic flux.
No.
So why are these figures 11 and 12 different is because figure 11 is looking into the polar direction of the star, where the magnetic field has an easier or simpler monotonic increase with energy density as shown here, but it could also be density. So inside the star is going towards the right in figure 11.
Right, here's the center.
Yeah, and you can see how the magnetic field doesn't increase linearly, but it's more like quadratically.
Yeah.
In a different paper, we actually fitted a formula for this that people can use if they don't want to bother with these general relativity codes. The references in the paper, you can just use this simple fit, which is a polynomial of B as a function of chemical potential.
Okay, nice.
But figure 12 shows how this is completely different for the equatorial direction, where it looks like the field has this weird bump there, followed by a more linear increase. And this is just a result of this kind of colloidal configuration where your Lorentz force has some non-trivial behavior around the equator. What will happen is that if you keep increasing this field, at some point, the largest the densest part of the star will actually come out from the middle.
Okay.
But we are not there yet because these fields are beyond realistic.
Okay.
We're keeping our limit to 10 to the 13 Gauss in the center, which is what virial theorems and this kind of calculation predict as a maximum value, realistic value for white dwarfs.
Got it.
But then our final result is showing in figure 13, which is what most people care about when they're talking about stars, which is look at their masses and radii. So before I was showing what happens inside one star, here we're looking at star families. So each curve is a family of stars with different central densities that are allowed by one equational state at one given temperature. And for this page here of work, we chose a magnetic field configuration given by this F0 here, which is your current constant. If you increase the current constant, we reach even higher magnetic fields, but we didn't want to do that because that's unrealistic. So if you look at the mass radius, maybe let's start the black one, which is kind of hiding behind the other colors.
But it's there.
Yeah, it's on the bottom.
Yeah.
So this line shows the zero temperature with or without magnetic field. And then what we showed is within these realistic magnetic fields, no matter the temperature that you have, you're not changing enough to have a different mass and radius that is allowed for stars, no matter the temperature. But if you increase enough the temperature, like the orange one / blue, which here signals the young white dwarf configuration, you see that in this case we get more mass just coming from this extra pressure related to the temperature. And a small exception for that is towards low mass stars, in which the magnetic field can make some difference here. You see that the lines with and without magnetic field, which are shown in the legend by having or not stars or asterisks, are changing a little bit. If you went to higher magnetic fields, the most massive stars will also change, but we decided not to go to. So this shows how temperature is actually more realistic. Higher temperatures are actually more important than realistic high magnetic fields for masses and radii. It doesn't mean that this is the same for other properties. We're focusing on this paper on these macroscopic structures, but there are other important quantities in stars that are very dependent on the magnetic field besides the temperature. So that goes a little bit into our next step, what we're going to do next. But before we go there, I don't know if Jeffrey wants to talk more about anything in this page that I forgot.
I have a question. 1.4 solar masses is sort of a famous limit. So you want to say anything about the effects of B fields on that limit?
So the Chandrasekhar limit was very debated a few years ago because people started finding out some very luminous supernovae, which is interested of the community here, I guess. And people started thinking, well, the magnetic field is very large. Does that change that a lot or not? The thing is that if you try to solve the tough equations, the Einstein's equation for the very specific case of spherical stars, and you try to add a huge magnetic field by hand there, what you're going to do is you're going to get a much larger effect on the mass than what's really realistic. So that's just coming from you trying to use a spherical symmetry for a case that's not spherical.
Got it. Okay.
So then you have no place to add pressure anisotropies in that equation. So if you just choose to add them positively,
Okay.
of course, you're going to get increase of mass. If you choose to add them negatively, you get a decrease. But neither of these things are realistic. What you should use is equations that take this anisotropy into account for you, which are just much more complicated solutions of Weiss's equations that you use here.
Okay.
And this is what brings the Chandrasekhar limit back to pretty much 1.4, as you can see in this plot for zero temperature stars. So it doesn't matter how high is your magnetic field, as long as you keep to what we call realistic. Maybe other people call different values, but this 10 to the 13 Gauss, if you keep to that value and do everything realistically, you do not go beyond 1.4, which is good or bad, depends on how you see it.
It's interesting either way.
The temperature changes it much more.
Oh, sure. Yeah, very cool. Nice. Okay, thanks for entertaining my comment there. Okay. Jeff, you want to say anything more about Fig 13? You want to move on?
No, I might want to comment that I don't know that 10 to the 13 would be a realistic case, more an extreme one. But other than that,
for white
a
dwarf.
limit.
Yeah, for white dwarfs, yeah, it's more the upper limit of possibility.
Okay, very good. Okay, and then we head out. That was it. Oh, at 13. Okay, very cool. Good. Jeff, Veronica, thank you very much for walking us through your very lovely article.
Can I actually say something more about concerning our outlook?
Yes, and that's where I'm going to go.
Oh, sorry.
So yeah, let's go in there. And so outlook. So very nice paper. Thank you. And so where do we go over the next, let's say, 2 to 5 years? Are there additional calculations can be done? Maybe there's already different calculations. This will get to Veronica's point about outlooks. So where do we go? What's the outlook from here?
Do you want to start, Jeffrey, and then I jump in later?
Well, we may have found someone to work to assist with white dwarf mergers with magnetic fields.
Ooh.
And we might have interest in cooling. We haven't found anyone for that though.
Okay.
So beyond, I don't know about the specifics on these yet though.
Okay. Mergers will be the perfect use of this kind of work, because when neutron stars merge, they get hot and their magnetic field increases besides increasing the density. So everything becomes more extreme. If compact stars are already extreme, then it becomes crazy extreme. And this is where this can become interesting, because then maybe the magnetic field can go even higher than 10 to the 13. Maybe the temperature can go even higher than the temperatures we're discussing. So things can get even more interesting. As far as I know, although neutron star mergers have been performed for the past, decade or so by several different groups, people are only starting to look into, for example, the merger of stars that are already very high in magnetic fields.
Okay.
Because as far as I understand, initially, for neutron stars, for example, the magnetic ones are always found in isolation. But as we're learning more about all the different systems that are there, it might become interesting to also look at magnetized stars in double systems and what could come out of that.
Yeah. Very cool. Very good. Sounds like a work plan for the next couple of years.
Yeah, no, Jeffrey's busy. I'm busy.
When are you graduating, Jeffrey?
Either this semester or in the summer.
Okay. I think merging stars will take longer than a semester.
Right.
Very cool. Very good. Well, I look forward in the coming years to seeing your additional outlook on these things with merging white dwarfs and other B field phenomena in white dwarfs. So, thank you very much again, Jeff and Veronica. Thank you. And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.